the ultraviolet spectrometer, and what we have is a small unit produced by Ocean Optics. It's called the Red Tide unit, USB 650 UV. So this is a little miniature UV visible spectrometer, and the software we need to run this little instrument is right up here. It's called Spectra Suite. So if we'll click on that, let it load. So Spectra Suite is a product made by Ocean Optics, and if it's all working properly, we should see an icon here of the unit that we're working with. Now, several things you'll need to do to get this up and running. Number one is to turn on the lamp, which is the ultraviolet visible lamp. Check that. Let's choose about 10 scans that we're going to average the output, and each scan is going to be 100 milliseconds long. Then we come down here and we'll see our output. This is in counts right now. We're going to change this to absorbance versus wavelength. So first thing to do is to check what we call the dark current. And we have a solid chunk of plastic here that we're going to place into the sample holder. And we come back up here and click on this what's called the dark current. So we click on that. Now the instrument knows what we think is no light making it to the detector. Then we're going to replace that with a sample of water. And then we're going to click on this light bulb here, which will be our reference for 100% intensity. We'll click on that. Now we can go over to the absorbance modes. We click on A, and our y-axis should change to absorbance or optical density, and the x-axis is the wavelength from 200 to about 850 or 900 angstroms. At that point, we are calibrated. Now, to double check here, let's go ahead and do our light current again. Make sure the instrument knows what is the light current. And we're going to use our block again. Block out the light, and then also check that. Make sure we know what the dark current is. We can go back, make sure we're reading 0. And to check the absorbance at any given wavelength, we can click within the screen here, and it'll show you the wavelength, and then the value of the optical density is displayed down here. So indeed, at 300, reading 0, 400, so it looks like it's properly zeroed throughout the range. To change the if you're doing ultraviolet, ultraviolet goes from 200 to 400 nanometers, and we can do that by coming up here to manually set the numeric range, which is the fourth icon from the left. So we click on that. The wavelength range 200, let's make this 400. And then normally we only show from 0 to 1, so we're going to put a 1 here for the maximum absorbance, and then apply that, close. So we should be 0 to 1 and 200 to 400. Now, one thing I want to illustrate here is the effect of different sample cuvettes. So right now I've got a cuvette that's made out of quartz. Notice that it has a kind of a frosted side. This is the side you want to hold, and the side that is clear, of course, is where the ultraviolet or visible light is going to go through. The way you put this into the instrument is you hold it on the sides or the top, and you place it into the instrument so that the clear side is in line with this arrow. So the light will be going through the clear portion of the cuvette. Now, the effect of different cuvettes can be illustrated in the following way. This is a cuvette supplied by Ocean Optics, but it has a narrower path length than the one that I was just using, and this is made out of plastic. And again, the way this goes in, you have a frosted side, and then you have the clear side. So the clear side would go in here. This is called their microcell. And if we were interested in, say, 280 compared to the previous tube which was made out of quartz, and we can stop this, pause it. The absorbance here is 0.325 compared to 0. The reason for this is because this is made out of plastic. So just keep that in mind. Different cuvettes will absorb different amounts of light. So if I was going to use this cuvette at 280, I would want to zero that at 280. Otherwise, it's absorbing almost 0.4 units of optical density. We could confuse that with our sample. Now we go over to another plastic cuvette, and this is the normal 1 centimeter thickness. Notice it has the edge here for holding, and then the clear side, so we place that in. And then go back to our scans. Now notice this is not near as nice of a tube, because at 280, let's go ahead and pause this again, we're well over 2. So it's absorbing almost all of the light at 200, or here's 280, sorry. At 280, 2.416. At 2.6, 2.492. It's essentially off scale. So this plastic cuvette, we learn, is essentially useless at 280 nanometers, often used for detecting proteins. The microcell from Ocean Optics could be used, but is not the ideal. And then I have another tube here, cuvette, made out of a much harder material, harder plastic. It's able to withstand acids and bases. If we take a look at that, again, it's almost off scale. So the lesson here is the ideal cuvette for work at 280 nanometers in the ultraviolet is the quartz cuvette. Notice the absorbance is 0. So that is the way you use this. And always have yourself a waste container to, if you're not keeping your samples, to dispose of those. And always rinse between runs with DI water. And it's often, the best procedure is, if you have a series of measurements at the same wavelength, to use the same cuvette each time. So that imperfections in the glass and differences in the absorbance tend to be canceled out if I use the same cuvette each time. Now the next video we'll talk about actually working with a protein, and we'll also talk about the visible range of the spectrum as well.